Okay, let's apply what we've seen already about affine transformations to prove that all ellipses are essentially the same under affine transformations. So this is section, let me use a more appropriate pen. So section 4.1, affine transformations of conic sections. Okay, so we want to see that any two ellipses could be transformed between each other by an affine transformation. Similarly, any two hyperbolae can be transformed by an affine transformation, and similarly any parabola. It'll turn out that you can't take one type of conic section under an affine transformation to another, but in fact all of these things become the same in projective geometry, and that will be the next thing that we do in the course, so section 5. But for the purposes of this, we'll see that ellipses are all the same under affine transformations. So without further ado, let's just crack on with proposition 4.5, which I'll state. I'll only do this for ellipses. The proofs are essentially all the same for the different types of conic sections, so I'll just go through the one about ellipses in detail. But do feel free, if you would like, to work out what the proof would be for the other types. So we're going to let C1 and C2 be ellipses in A squared. Then there is an affine transformation F such that a point P is in the first ellipse if and only if the image of the point under F is in the second ellipse. Right. So the proof, which I simplified from the previous version of these notes, is slightly different. What we're going to do, it's a fairly standard technique. If you want to show that two things can be transformed from one to another under a set of transformations, then it's often quite good to start with one that you know very well and transform that to an arbitrary one. And if you can do that, then you can always start from one of them, go back to the one that you know, and then go onwards to the one that you're interested in. So let me write that down in a more clear manner. So we will prove that there exists an affine transformation F such that F of C is C1, where C is the unit circle in some coordinate system xy of an, A2. So this is implicitly telling us that there is an origin here, which is 0, 0. Then the idea will be that we take the unit circle in this coordinate system, and if there is some ellipse, which could be sort of facing in a different direction, we can take, if we can work out how to take f to c1 like that, then if c1 is arbitrary, then we also know that we have a g that can take us to some other ellipse. Might perhaps look like that, c2. And so what you'll do, in fact, on one of the exercise sheets is show that if f isn't a linear, if f is an affine transformation, then f inverse will also be an affine transformation, and if you can compose two affine transformations, you also get another one. So if I first do f to the minus 1 to get me back to the circle, and then do g of that, compose it with g, then I'll get to c2, and that will give me an affine transformation, which is g composed with f to the minus 1. That will take me from c1 to c. So it suffices just to do this case where I move from c to c1. Okay, and the nice thing about doing the transformation from c to c1 is that once I've done a translation, the same equation is going to, essentially the same equation that defines c is going to define the image of c under the translation. So let's first use a proposition that we've proved already, which is this. So by proposition 3.6, there is a coordinate system of A2, which I'll call UV, such that C1 is just expressed in the usual way according to that system. So C1 be equal to the set of UV such that u squared over a squared plus v squared over b squared is equal to 1. Now that's one thing that we did earlier on. Now we also have that C is the set of x, y, so just going back to this unit circle, such that x squared plus y squared is 1. Okay, so we want to know how to move from this coordinate system xy to a coordinate system here, which will be, so we'll have a u and a v, something like that. We want to know what that origin is, and that's going to be q. For me, let me just show you, sure you can see that. So this is my xy coordinate system, and that's my uv coordinate system with an origin there, q. So with q, the origin of the uv system, I have that C plus Q is obviously going to be a unit circle, because translation of a unit circle is still a unit circle, but now it's based at the origin of Q, of the UV system. So if I call that C dashed, then I can express that simply as saying that it's the set of uv such that u squared plus v squared is equal to 1. So the nice thing is I don't need to worry about what direction the unit vectors u and v are pointing in, because I'll always get the same equation of the circle there. Makes this just a little bit simpler. Okay, well, all we now need to do is to work out how to stretch the unit circle so that it gives us the ellipse that we're after. And I can do that, as it turns out, with an invertible linear transformation. So let M be a matrix which just scales u and v appropriately. So I want to scale u by a and v by b. Then u dashed v dashed, so if I let u dashed v dashed be equal to m times uv, then my u dashed and v dashed are going to be just au and bv. Now we want to know what equation is going to be satisfied by AUBV. We know that u and v satisfy the equation of the circle, so u squared plus v squared is 1. But then if you plug u dashed and v dashed into the defining equation C1 here, so if I plug u dashed and v dashed in there, you're going to see that precisely what happens is that the a and the b cancel from the top and bottom of this fraction, and then I do get the point that was satisfied by the original point under before I applied this transformation. So we have that u dashed v dashed satisfies u dashed squared over a squared plus v dashed squared over b squared is, plugging these in, just u squared and then because the a's cancel, and b squared v squared over b squared, which is just again v squared, and we know that these points which were on the circle satisfy 1, and so u dash v dashed is on C1 as required. So right, and so now we'll just put all that together to work out what the affine transformation is. So therefore f of p, if we define that to be equal to, so we're first going to take p and translate it, and then we're going to apply m to it. So it's going to be m of p plus q. So the q first takes us from the circle to the new circle, c dashed, and then we apply m to it, and it turns us into the this appropriate ellipse. So that's going to be m dot p plus m times q. So that's our translation vector relative to the coordinate system uv. So this is an affine transformation taking C to C1 as required. Okay, very good. So as I said, I'm only going to do this for the ellipses. I will just state the result for the hyperbolas and parabolas, but they are very much as you would expect. So proposition 4.6 is if C1 and C2 are hyperbolas in A2, then there exists f such that P is in C1 if and only if f of P is in C2. And proposition 4.7 is going to be just exactly the same thing for parabolas. So our parabolas, and then exactly the same statement. Okay. Let's use what we've now said about hyperbolas to say something about, affine transformations on the ellipses to say something about the areas of them. And that's going to come out entirely from the fact that we have a transformation whose determinant we can calculate. So let's calculate the area inside the ellipse C, which will just be given by this defining equation. So the xy such that x squared over a squared plus y squared over b squared is 1. So going back to the proof of the proposition 4.5, we saw that we could get from the unit circle, which has area pi, to this ellipse if we applied a scaling operator m. So the proof of 4.5 shows that we get from the unit circle to C by possibly a translation and then a scaling operator. M, which was equal to AB. Now we know how linear operators affect area. They affect the area by changing them by a factor equal to the determinant of those linear operators. So if we know what the area of a unit circle is, then we know what the area of an ellipse is, because we're just going to multiply it by the determinant of this. So since the area of the unit circle is pi r squared, but r is 1, so since the area of the unit circle is pi, the area inside the ellipse is just det m times pi, which is equal to a times b times pi. Okay. Now it's fairly easy to see that the only conic sections are that have finite area are going to be the ones which are ellipses, because the area inside a hyperbola is, or inside a parabola, is obviously going to be infinite. So that proves one part of theorem 4.9, which I'll state, which is just going to say that you can't move between different types of conic sections with affine transformations. So theorem 4.9, let C be a conic section and F sending A2 to A2, an affine transformation. Then C an ellipse if and only if f of C is an ellipse. And similarly with the other types. I suppose if we were living in the 19th century, one would write an hyperbola, but anyway, it's C a hyperbola if and only if f of C a hyperbola, and similarly C a parabola if and only if f of C a parabola. Okay, so we're not proving this theorem, but it is clear that if you have C an ellipse and you apply an affine transformation to it, then you will get another ellipse. Because you can see how the coordinate system changes under F. What isn't clear is that if you take any conic section whatsoever and apply a transformation, that you couldn't somehow go between the two. So one direction of this is more straightforward than others. Fundamentally, the way you want to prove this is by classifying quadratic forms. So this isn't, again, something that we're going to do here, but it's something that you can look up if you would like. But at least we can see from the calculation of the area that we've already done. So at least we can see that since F sends finite areas to finite areas, we cannot map ellipses to hyperbolas or parabolas, or vice versa. Right. I will finish with just a comment about why you can't send hyperbolas to parabolas, which can be turned into a proof. The point there is that if you take the tangent lines to the hyperbola that are perpendicular to the line through the foci, then you will get parallel lines that contain a single point of the hyperbola, and you can't have that situation with a parabola. So if you would like to draw a picture of that and convince yourself that that's not going to be a possible affine transformation, that would be a good exercise. Okay, and we will stop there.